Mother Teresa once said, I alone cannot change the world, but I can only lay the first stone to create many ripples. With this quote in our hearts, I, Shakal Lamitra, on behalf of the AI division of VIT Bhopal, would like to extend a warm and gracious good afternoon to all present today at the webinar on fuzzy clustering and its collaborative fuzzy clustering and its applications. As quoted by Martin Luther King Jr., take the first step. You don't need to see the entire staircase. Just take the first step. So stepping on the first stone, hoping to learn a lot from this insightful webinar, I would like to request our AI division head, Mr. S. Swandarajan, to address the gathering.
Good afternoon, Honorable Present here. So I welcome Mukesh Prasad, sir, actually School of Computer Science Center for AI, Faculty Engineering and IT, University of Technology, Sydney, Australia. So given acceptance for this particular webinar, so given the topic collaborative fuzzy clustering and its application to our VIT Bhopal students and faculty. So I welcome you, sir, for given a wonderful webinar for next 1.5 hours. And I welcome Dr. S. Pungundran, Dean SESC, and I welcome Dr. Nilamada Mishra, so this coordinator of this webinar, and other faculty members and students. Welcome you for once again for this webinar here. So now AI is a buzzword for all industry. So everybody wants to learn artificial intelligence applications for applying everywhere the solutions, and then industry migrations and software migrations is most important. So most of the students nowadays, it is required to learn this kind of technology for trending in machine learning and deep learning and neural networks. So it will be giving a lot of hope to getting more jobs opportunities in the future. So I thank Mukesh Prasad sir for a wonderful opportunity given for this kind of webinar for all the students in the AI division. So I thank you, sir, and I'll thank Nilamada Mishra for arranging for this workshop. So thank you for all for this. All of you, I hope enjoying for this webinar. Thank you.
Thank you very much, sir. I would now like to invite our Dean SCSC, Dr. S. Poonputran, sir, to share a few words.
Yeah. Are you able to hear me?
Yes, sir.
Yeah. Okay. Thank you. The respected today speaker of program, Dr. Mukesh Prasad from University of Technology, Sydney, Australia. The division head of AI division, Dr. Soundararajan. The organizing crew of this program, Dr. Soundararajan and Dr. Nilamada Mishra, and other professors and students and organizing crew members. Very warm good afternoon to every one of you. I'm very delighted to be here and take part of this today workshop on collaborative fuzzy clustering and its application. So sometimes back, I had an idea like, so whenever we are talking about AI, so usually we had a course called soft computing, and that will be taught in last 10 years. While we are teaching the soft computing, I could say that evolution. So initially the soft computing will be taught in three things. One is a genetic, another is a neural system, another is a fuzzy logic. And slowly when we are moving into deep learning and this neural have evolved to deep learning based solutions. And somehow the picture of fuzzy logic is missing. Okay, so that was a reason my observation. So we had of thinking of that, and we were able to incorporate it to different area. Okay, and then finally we ended up in a very beautiful program today. So I'm very happy to see this particular title, and I'm very much excited to see the further exploration on this fuzzy logic. Because I just wanted to cite few things only. Okay, so I don't want to take much of the time. So already the speakers are with us, and they will be taking us to the fuzzy logic in a different aspects. Okay, so fuzzy logic, if you see that this is a different logical theory which has been developed in 60s, and initially it has not been accepted by many of us, And first, the Japan have accepted because this particular logic has been introduced in contradiction to that our existing binary logic. So where we deal everything with the binary logic of zeros and ones. Then fuzzy logic brings the notion of called degrees of membership. So where we were able to map the relation between 0 to 1. So which is really mapping into real-time scenario, and that triggered a lot of innovations in this particular line. But initially it has not been accepted by many of us. The moment the Japan have taken and accepted this logic, and recently now we can see many researchers are evolving in this fuzzy logic. Okay, and definitely it is a very strong feel that this fuzzy logic will play a vital role in AI also, because AI is evolved in terms of data science and other areas where we saw about neural systems in a over of layer of optimization. Then we went for deep learning. So every layer wise optimization. Okay. So now if you could add with this fuzzy logic, and definitely this will lead the better results and better innovations will come. And this is very, very sure. Okay. So this is only one point I just wish to share at this junction. So with this word, I wish you all the best of this event. I request all the participants to please interact with the speaker to get as much as possible outcomes and takeaway. Wish you all the best. Thank you and thank you.
Thank you very much, sir, for your insightful words that paved a strong foundation for all our audience attending this webinar. Now, moving on, I would now like to request Dr. Nilamadhav Mishra, sir, to introduce our speaker of the day.
Okay. So, revered all the dignitaries over here, and good afternoon to everyone. So now I'm going to introduce Dr. Mukesh Prasad. So who is a senior assistant professor at School of Computer Science in the Faculty of Engineering and IT at University of Technology, Sydney. Yeah, so this is one of the, we can say the top 133 university in the world, in the particularly as for the QS academic ranking. Okay, and he has made the substantial contributions to the field of machine learning and AI, and also the Internet of Things. So his research interests include all the big data, particularly computer vision, the brain-computer interface, evolutionary computations. He's working also in the evolving and increasing important field of image processing, data analytics, and edge computing. So which promise to pave the way for evolutions of new applications and services in the area of healthcare, biomedical, agricultural, smart cities, education, marketing, and finance. So his research has appeared in numerous prestigious journals, including IEEE and SCM transactions and at conferences, and he has written more than 120 research papers. So he started his academic career as a lecturer at UTS in 2017 and became a core member of university's world-leading Australian Artificial Intelligence Institute, which has a vision to develop theoretical foundations and advanced technology for AI and to drive progress in related areas. So his research is backed by industry experience, specifically in Taiwan. So where he was the principal engineer at the Taiwan Semiconductor Manufacturing Company, TSMC. So there he developed the new algorithm for image processing, pattern recognitions using machine learning technique. He was also a postdoctoral researcher leading to the big data and computer vision team at National Chiao Tung University, Taiwan. So he received a MS degree from India and the PhD from the Department of Computer Science at National Chiao Tung University, Taiwan. And his mainly the research interest arise on particularly spreads on the machine learning, data analytics, artificial intelligence, computer vision, brain-computer interface, and Internet of Things. So let's welcome to our speaker, Dr. Mukesh Prasad. Mukesh, sir, please.
Yeah, thank you, Dr. Misra, for your brief introduction. I think you already briefly described my background, and however, I will. When I start my presentation, I will also take a 2 to 3 minutes to introduce myself in details. And also I would like to extend my thanks to Dr. Sundarajan and the Punakutram. So I think Dr. Punakutram already explained some basic things behind the fuzzy logic. So fuzzy logic is not new, and so it's been introduced back in 19th, but initially, as Dr. mentioned, initially it was not accepted, but when the Japan they accepted, particularly in the application in the control area. So, but now you can see fuzzy logic has been applied everywhere, not only in the control area, but into the civil engineering, electrical engineering, in agriculture, biomedical, and so on. And you can see the fuzzy logic. I mean, most of us, we are using electronics devices such as washing machine, refrigerator, and so on. So the logic behind those control system, they use the fuzzy logic. So you might not aware what kind of mechanism they use, but if you go and look at the technology, so they have been fuzzy logic has been applied in those control systems. So yeah, so most of the biggest company like Hitachi, Samsung, Sony, even NASA uses the fuzzy logic to reduce the fuel consumption and so on. So there are lots many application of fuzzy logic, but we need to know how to apply in a right direction. So today, my talk is more focused on the research side, because nowadays people just talk about the application of AI and machine learning. So I'll be focused more on the research side. So the today topic title is collaborative fuzzy clustering and its application. And so so these are the outline for today's topic. I will go through some motivation behind this research topic, then give a brief introduction about the fuzzy C-mean clustering, and then I talk about the collaborative fuzzy clustering, and then pre-process collaborative fuzzy clustering. And then I will talk how we can use collaborative fuzzy clustering combined with the neural network, especially for the neural fuzzy inference system. And then I will also discuss how we can apply the collaborative fuzzy clustering with the two main important and the mostly used inference system, that's Mamdani and Takaji Sukono Khan type models. And then I'll go through a couple of the experimental results, and then I conclude my session. Yeah, so before I'm going to start my presentation, I would like to introduce myself. So my name is Mukesh Prasad, and I'm born and brought up in India, is part of India, that's Bihar, where I finished my basic education till my undergraduate in my village. Then I cracked the entrance exam of JNU, that's Jawaharlal Nehru University, for the MCA degree, that Master of Computer Application. And after studying my Master of Computer Application, I completed that degree in 2019. Then I worked as a software engineer for 1 year in Delhi itself. Then recession hit, and then I thought, okay, let's go for higher study. And then I applied for a couple of scholarship, and then I got a scholarship for the Taiwan. So I think during that time, Taiwan was even not known to many people. When you talk about the Taiwan, usually people, they say Taliban or Thailand. So that was a different scenario. But I think, but most of us, we are using the electronics device, and the chip inside that those electronic devices are basically made in Taiwan. And also if you are aware, Taiwan has a very big electronics hub, and the Asus and Acer are from Taiwan itself. And so, and the world biggest semiconductor manufacturing company is in Taiwan itself. So that produces and supply the semiconductor, the chip around the world. Okay, so then I went to Taiwan to do my PhD in Department of Computer Science in 2010, and I completed my PhD in 2015. And during my PhD, I met with Dr. Nilam Dam. And yeah, so we just met, I think, 1 or 2 times, just for a couple of hours, and we had discussion. And since then, I think we are in touch and we know each other. So after I finished my PhD, I joined the Taiwan Manufacturing Company, Semiconductor Manufacturing Company, in 2015 as a principal engineer, and I worked there for one year, and then I got offer for the academia to join University of Technology Sydney in 2017, and since then I'm in academic, working in the area of machine learning, AI, and big data. Basically, I work with the algorithm side. So we develop a new algorithm, and then we apply this algorithm to many different areas such as healthcare, marketing, finance, education, agriculture, image processing, and so on. Yeah, so that's a very brief introduction. Now let's jump to the topic. Okay, so the motivation behind this research topic, I think most of nowadays, most of the organization, they want to improve their let's say mm, their sale. So they want to collaborate with the other company to know more about the customer. So if they can know more about the customer, so accordingly they can tweak their product and they can sell to the customers. So nowadays, I think our all informations are not hidden. I think information are now shared by many different. So once you provide your information to any particular organization, usually there is a highly chance they can sell or they can share your information to the other customer for the other business purposes. So but again, if you want to share your customer information directly to the any company, there is some privacy and security concern that's need to be dealt. So of course, the customer details basically it's include their basic information alongside with their daily activity, like what kind of product they are purchasing, what kind of services they are availing, and so on. So because of this privacy and security concern, nowadays many people they are focusing and proposing new techniques to deal with these kind of problems. So with this research, we also focused on how to preserve the privacy and security and while sharing the information to the other organization. So although we don't have the real world data to do the experiment, but whatever data we have, we did some experiment and we have shown like how we can preserve the privacy and security and while sharing the information with the different organization. So also we propose collaborative fuzzy clustering, and then we propose the pre-process collaborative fuzzy clustering techniques that can helps to preserve the privacy and security of the data set itself. Also, nowadays, big data analysis, because data is getting bigger and bigger every day, every second, due to the social media uses or due to the Internet of Things. So the data is becoming bigger and bigger. So also, and doing the analysis of data is getting much harder. And also recently, the transfer learning, another research focus. So if you are focusing on the deep learning or AI side, so you must be familiar with the transfer learning. So these are the other two motivation where we can apply collaborative fuzzy clustering to deal with this kind of problems in different area in the finance forecasting, biomedical, social media, and the other engineering things. Yeah, so these the proposed methods. It's focused to deal with the problem with in terms of the volume. So because as I said, the volume of data is increasing every second, every minute, every hour. So day by day the volume is increasing, and handling this kind of data is again a problem. So we are going to talk how we can just use the small portion of data that can help us to solve, that can help us to give some comparative result. When I say comparative, that means it will give either a better result or it's a similar result when you use the whole set of the data set. So later we will talk more on that part. And yeah, and also I will give the application how we can apply the collaborative fuzzy the clustering in the area of inference system. So I will go through the fuzzy first, how we can combine the neural inference system with the fuzzy, as well as Mamdani and TSK models with the collaborative fuzzy clustering. And we'll go through couple of the experimental results, and then we can validate the result through some matrix. Yeah, so if you have taken the soft computing or any machine learning, the fundamental course, you must be aware about the fuzzy C-mean clustering. So in basically in machine learning, so there machine learning, there are two kind of learning mechanism. One is called supervised machine learning, and second one is called unsupervised machine learning techniques. So I will not go in details about what is a supervised machine learning and supervised machine learning, but I will give a very brief idea. So a supervised machine learning, basically when we have the input data and the corresponding output, that how you can apply it based on the training and the testing and validation set. So unsupervised learning, you don't have any output, you just have the input, and using the input, you need to look for some kind of knowledge, some kind of relation among the data set itself. So fuzzy C-mean clustering, also the unsupervised machine learning. So clustering is one of the part of the unsupervised machine learning techniques. And within clustering, there are two kind of clustering. One is the hard clustering, and the second one is the soft clustering. So in the hard clustering, basically, you just have the output directly, whether it's yes or no. So whether that particular data points is belong to one cluster or to the another cluster. So there is no member, so that's called hard clustering. Either that particular data points belong to one class or to the other class. But with the soft clustering, so soft clustering basically deal with the membership value. So that means one data points can belong to some, let's say 80% belong to one cluster, and 20% it can belong to the another cluster. So it's based on the membership. So let's say if I take a membership of some particular things, maybe my membership 90% I'm member of that one club, and 10% membership with the other club. So this is how the membership works, and this is how the soft clustering works. So in 1981, Benzek introduces the fuzzy C-mean clustering, and the whole idea for is to introduce the membership functions that can each data point exhibits to one or more than one cluster of that at a specific membership function. So the objective behind fuzzy C-mean clustering is defined with these objective functions. So where we can discuss more. So where M is your the real number greater than 1, and UIJ is a degree of membership value of a data point xi, and in the cluster J. So there are J number of cluster, so that data points belong to J number of clusters, and where xi is the ith data point of the d-dimensional data, and vj is the dimension of the cluster, and this symbol is just a normal expression similarity between the measured data and the cluster. So the whole idea to optimize this objective function to update the centroid and the membership, to calculate the membership value. So yeah, so let me just move on. So this is the basic procedure for the fuzzy c-mean clustering. So once you have the given data set, you need to define the number of clusters. So number of cluster is a user defined. So you can see set the value of c, that's a number of cluster, and then you need to initially define the prototype, that's v1, v2, v3, that is depend on the how many cluster you want. So that's called the prototype based on, and that is from the given data points. So once you defined the number of cluster and initialize the prototype, then now you need to compute the distance of the each data points with the initialized prototype. So this is how you can compute the distance, and this distance is basically we use as the Euclidean distance. So I think you guys must be familiar how to calculate the Euclidean distance. So now once you compute, and then it's find the minimum compute the partition matrix, that's the membership value. So you can use this equation to compute the membership value for the each data points. So this, you can see how it has been formulated. So it will go from the 1 to number of clusters, and it's a take a distance for the defined each centroid. And so once you compute the membership value, then you need to update the prototype. So that's the initial prototype you have defined. Now you can update that prototype with this given formulas. So this is your membership value, and this is your the value of data points, and n is so this is a sum of 1 is equal to 1 to n. That's n is an n number of data points. So now this is an iterative process, and it will goes on, and so but you need to define some stopping criteria to stop this the whole process. So either you can define some conversion, or you can define the number of iteration, limit the number of iteration. So once the number of iteration reaches, the whole program will stop and it will give the output. Otherwise it will just go to the step 3, that's here. Then again it will compute and it goes on. So this is just an initial pictorial representation how fuzzy c-mean clustering works. So this is a scatter plot, basically a plot of the given data points. And now you can see when you choose the number of cluster 2, so you can see how your whole data points has been divided into 2 different clusters. So you can see the cluster 1 that is represent with the circle green, and the another cluster that's represent with the red plus. So you can see how your data point has been divided into 2 different clusters based on the number of cluster you defined. And the bottom right plot, it's defined how the conversions is happening. So you can see, let's say you define the number of iteration 100, but you can see once the conversions become very steady, and then there is no much differences. So that's why it's a stop even at the probably 26 or 28 iteration. So you need to define this number of iteration and also the conversions, the value. So this is just a result based on the number of cluster 2. Then similarly, you can see this diagram represent how when you change the number of cluster from 2 to 3 and 2 to 4, this is how the clusters look like. So when you define the number of clusters 3, you can see the whole data set is divided into 3 different clusters. And the big circle, the black, is represent the centroid of that clusters. And again, this star is centroid of this cluster, and this plus sign is the centroid of this cluster. And this is again, this is an iteration. You can see the convergence rate. So you can see when you choose the number of clusters 3, now the whole program run till around 55 iterations. So that's a convergence. And similarly for when you choose the number of cluster 4, so you can see this is how the fuzzy C-mean clusterings give you 3 different clusters based on defined number of clusters. And again, this is the bottom right plot is to represent the iteration or the convergence of the whole program. So this is just a basic description of the fuzzy C-mean clustering and the output. Now I'll talk a bit of the collaborative fuzzy C-mean clustering. So the fuzzy C-mean clustering is only suitable to handle one set of data set at one time. And so collaborative fuzzy clustering concern a process of revealing the structure becoming more common and similar to the number of subset of the data set. So now now the whole idea behind the collaborative fuzzy C-mean clustering. So let's say you have two different data sets. Let's say two organizations have a data set of a particular customer, and they collected the information and they would like to share. So what they can do, they can locally do the clustering. So once you clustering, as you know, when you do the clustering, so it will give you just a membership value, and in terms of the membership value and the centroid. So once you have the membership value and the centroid, that doesn't contain the actual information of the data set. So now once you perform the clustering locally on individual data sets, now you can collaborate globally by exchanging the information about their findings. So once you perform the fuzzy C-mean clustering locally, and now you can share the information in terms of the membership value and the prototype. So that's how you can preserve basically privacy and data confidentiality, and it's also solve the security issue as well, because you are not going to share the original information of the data. So the data set you are going to share is in terms of the membership value and the prototype. Now, once you share those information to the other client or other service provider, now those prototype and the membership value need to be communicate each other and try to get some information among themselves, and then they update their information based on the others information. So basically the collaborative fuzzy clustering can be divided into two different types. The first one is called horizontal collaborative fuzzy clustering, and second one is called vertical collaborative fuzzy C-mean clustering. So if you look at the the data set carefully. So let's say you have two different data sets. So basically data set contains two kind of information. One is a number of columns and number of rows. So number of columns is your the features of that particular data set, and number of rows is called the samples or the value of that data set. So sometime what happened, maybe one organization collecting a data into different format and other organization collecting in data in different format. So if you collect the data into different format, it would be hard to collaborate and get information. So you need to see the structure of the data, and accordingly you can adopt the different collaborative fuzzy clustering. So let's say if your data set, if the given data set of two different organizations having the same number of patterns but different number of features, that means the number of features, the number of columns are different, and but the number of rows are same. So in that case, you can use the horizontal collaborative fuzzy clustering. And if if the data set having the different number of patterns but the same number of features, that means the number of column is the same, but the number of rows are different, then in that case, you can use the vertical collaborative fuzzy clusterings. So now the figure C is represent basically the schema of the how two different data set can collaborate each other. So let's say we have a two different data set L and data set M. Now we compute the membership value and the prototype for each data set separately. Now we want to collaborate. So beta is your coefficient, the collaboration coefficient. That's again the user defined. That value is a greater than 0, so it should be positive value. So the notation beta M and L, that means the collaboration, that means the data set M wants to collaborate with data set L, and the notation that's present beta LM, and that means the data set L wants to collaborate with data set M. So this is how you can we can describe this notation in a different way. So so if particular data set wants to collaborate, we need to change the notation of that particular collaboration mechanism. Okay, so the whole idea for the collaborative fuzzy clustering, again, as we know, the objective function for the fuzzy C-mean clustering, the initial objective function is basically original fuzzy C-mean clusterings. So we proposes the new objective function with the combination of the second objective function you can see. So the new objective function is defined at Q and L. That means dataset L wants to collaborate with dataset M. So in this case, you can see, so again, we need to optimize this whole objective function. So optimizing an objective function is, if you are familiar with the optimization techniques or operation research, and that's one of the mathematics course, then you will be able to optimize and find this updated partition matrix and the prototype. So you need to use some kind of Lagrangian mechanism, some other mechanism, which we can minimize this function. So for the minimization, only we have two kind of minimize. Only we can minimize or maximize. So so we have only two optimization problem that we need to solve. So now, so this is the objective function that we want to use to get the updated partition matrix and the updated prototype. And so once you optimize this whole objective function, you'll get this updated partition matrix and this updated prototype. So I will just briefly go through how we can optimize this objective function. I know some of you, it would be difficult for you to understand at this stage, but once you get familiar with this technique, you will be easily optimize and come up with this updated partition matrix and the prototype. Yeah, so as I said, so beta is your user defined value that's greater than 0. So in order to optimize this objective function, we are going to use the Lagrange multiplier techniques and to determine the partition matrix in order to make the constant free optimization, because we want to get the updated partition matrix, and where this lambda define the Lagrange multiplier. So this is how we are going to introduce the Lagrange multiplier that will help us to get the updated partition matrix. And once you get the updated partition matrix, we can compute the updated prototype. So basically what we need to do, we need to do the differentiation. So if you guys are good with mathematics, so this is basically this calculation. So this is a differentiation with respect to the partition matrix, that's 0, and this is the differentiation with respect to the Lagrange multiplier, that's 0. So now we need to do the differentiation, differentiate this whole objective function with respect to the partition matrix. So how we did that. And then once you compute this one, then you'll get the updated partition matrix. But there are a couple of steps more involved that I think you guys will be familiar to solve it. So I'm just going through a the final output of the updated partition matrix here. So once you differentiate this objective function, you'll get the updated partition matrix. And similarly, with the updated partition matrix, now we need to do the equilibrium distance to compute the prototype of that objective function. So and this is how we can again use and apply the updated prototype and update the expression, and you will get the updated prototype of this one. So don't worry too much on this mathematical equation. Okay, so this is the basic procedure for the collaborative fuzzy C-mean clustering. So initial steps are basically your fuzzy C-mean clustering. So we propose one more step that's called a step phase 2, where you need to do the collaboration. So once you get the updated partition matrix and prototype, now you need to define the collaborative coefficients, and then update your prototype and partition matrix of your own data set based on your the other data set, and then you run this whole process till the termination condition has finished. So okay, so you can see this is how the collaborative fuzzy clustering looks like. So this is your attribute 1, that is a data set 1 and data set 2. So this is your initial clusterings when you perform the fuzzy C-mean clustering. So how the clusterings look like for data set 1 and data set 2. Now let's see when these two the data set collaborate to each other through the fuzzy C-mean clustering using the collaborative fuzzy clustering mechanism. So we can see there is a changes in their structure, initial structure. So we use beta is equal to 0.5. So that's a collaborative coefficient value. And so you can see after the collaboration, so when the data set 1 collaborate with data set 2, there is some changes in the structure. So you can see the dark dotted line is the updated clusters after the collaboration. So initially you can see these two data points where belong to this cluster, but after collaboration, now it's merged with this cluster, so another cluster. So, and you can see also there is a structural changes in the cluster data set 2 as well. So after the collaboration, you can see how the cluster, the structure of the cluster has changed. So you can see initially there is only one data points in this cluster, but after the collaboration, you can see this cluster has been extended and contain the other data points of this cluster. So especially the 4, 8, and 5 data points have merged with this the third clusters. So this is how you can basically visualize the effect of the collaborative fuzzy C-mean clusterings. But again, you need to do the validation whether the cluster based on the collaborative fuzzy C-mean clustering is really making sense or not. So there are two different way you can validate your cluster. So first one is your partition coefficient, and the second one is called classification entropy. So once you use the partition coefficient, then you will be able to say, okay, now the cluster validation is better than the before. Yeah. So we applied these two matrix that's called the partition coefficient and the classification entropy. So you can see these are the initial partition coefficient and the classification entropy of the data set 1, and this is the initial value for the data set 2, that is value before collaboration. So this result is based on basically collaboration coefficient 0.2. And you can see, so after collaboration, you can see there is some changes in the partition coefficient and the classification entropy. So you can see after collaboration, the partition coefficient value has been increased. So that means if partition coefficient value is closer to 1, that's indicate the cluster is a good cluster. And if the classification entropy is closer to 0, that's indicate the better clustering results. So you can see after the collaboration between dataset 1 and dataset 2, the validation results has been improved. So you can see, yes, there is a need of the collaboration, and that can really help to validate the clusters clearly. And this is just another way to represent the represent and see the effect of the collaborative clusterings. So you can say this is your initial partition matrix of dataset 1, and you can see how the value has been changed from this to this value after the collaboration. So you can see, okay, yeah, there are some changes in the partition matrix as well. And this is a partition matrix of the data set 2. You can see there are some changes in the partition matrix 2 as well. Similarly, you can visualize the changes in the prototype. So you can see there are 3 different clusters, and these are the value of the prototype before clustering, before collaboration, and this is after collab. So you can see there is a shift in the centroid as well after collaboration. So this is just a way to visualize some values which can use and present. Okay, so yeah, before yeah, so there is some problem with the collaborative fuzzy C-mean clustering. Further, we propose pre-process techniques to solve this issue. So the fuzzy C-mean the fuzzy C-mean clusterings works in a very random manner. So every time when you initialize the clusters, you can see see the different segments of the cluster. So maybe initially you have cluster 1, 2, 3, but when you do the second round, then you will have the cluster 2, 1, 3, right? So there is no such order of the clustering. So when you do collaborate, so there are a highly chance, so one particular cluster of one data, let's say cluster 1 may not communicate with the cluster 1 of the data set 2. So to deal with this problem, we propose pre-process techniques that help us to minimize the risk. So what we did basically, in order to make the order of the cluster for in two different data set, we compute the distance of this cluster 1 to cluster 2 and find the minimum distance, and then we reorder the cluster. So while doing this one, we'll have the same order. Let's say cluster 1 to 2, 1 to 3 for data set 1, and then we'll have the same order for cluster 1 to 3 for the data set. Then it will be easier for us to take the difference between the two clusters. So this is how we can, so this is another way to express what is the problem with the collaborative fuzzy clustering and how we solve this problem using the pre-processed collaborative fuzzy clustering. So let's say you have the original data set. Once you divide a data set into, let's say, n number of data sets, and when you perform the locally cluster on each data set, so let's say this is your, when you perform the fuzzy C-mean clustering on each data set. So you might have data cluster 1, cluster 2, cluster n, and this data set can have the cluster A and cluster 3. But when you do the collaboration, so there are highly chance your cluster 1 may not communicate with the cluster 1 because the order is different here. So we need to fix this order first before doing the collaborative fuzzy C-mean clustering. So if you do the pre-process, so you can see after pre-process, we match the order of the clusterings here. So now it will be easier to communicate cluster 1 of this data set with the cluster 1 of this data set. So while doing this, we can basically reduce the risk of the misinterpretation of the data set. So, and this is another visualization representation where we can see what is the effect of the pre-processed collaborative clustering. So you can see this is your the initial clusterings. So you can see, so this is a random initialization. So as I said, let's say this is your cluster 1, but this cluster 1 in these clusters become cluster 2 here. So we need to fix this order, so it will be easier for us to communicate the cluster each other. So this is the initial clustering for dataset 1, and this is the initial clustering for dataset 2. So now we need to perform the pre-processing. Basically, we need to do the mapping. So once you map, so you can see after mapping, we can reorder the cluster of the dataset 1. So after mapping, you can see now we reordered the clusters. So now it will be easier. So you can say if this is a cluster 1, so you can see the similar things. We can have the cluster 1 in the data set. So now we can easy to communicate and take a difference between the cluster 1 of dataset 1 and cluster 1 of the dataset 2. So basically pre-process helps to reorder the clusters. Okay, but again we need to validate how we can prove, okay, this proposed mechanism is going to work or not. So as you remember, so basically we added another steps in this the collaborative fuzzy clustering. So in this phase, so phase 1 and phase 3 is remain the same, but we incorporated the another phase, which basically compute the minimum distance of the prototype, the centroid here, and we find, and then we reorder the whole clusters. And then, yeah, so we do the again iterative process and yeah, wait for the execution of the program. Again, how to prove this pre-process is going to work or not. So we use a degree of approximation that's help us to kind of do evaluate the proposed methods. So we need to compute the difference between the prototype of the dataset 1 and dataset 2. So the smaller the value of theta is the more similarity between the membership value of dataset L and the dataset M. Yeah, so here we can see these are the results. So the beta is your collaborative coefficient. So use a different collaborative coefficient to do some experiment. And this is your original value for the collaborative coefficient. And this is your pre-processed one. So you can see this value is more smaller than these two value. That means the degree of approximation is better. So that means the reordering is going to help us to find the better clustering approach. Similarly, so these are the two different data set we use. So this is the result based on the ARIS data. ARIS data is a very famous data set if you are working with the machine learning technique. So this is a very easy data set to understand the whole process. And these are the another data sets called Mackie-Glass data set. So we perform the experiment on this data set to just to validate the proposed mechanism, and we figure it out. Yes, it's working the right way. Okay, and yeah, so this is another way to the whole process, how the initial plot of the scatter plot of the data set, when you perform the fuzzy C-mean clusterings, when you apply the collaborative fuzzy clustering with the data set 2, and when you apply the pre-process collaborative clustering after the collaboration. So you can see there is a difference. So you can see now our initial structure of or order of the clusters matches with the after applying the pre-process fuzzy C-mean clusterings. Okay, similarly, when the dataset 2 collaborate with dataset 1, so this is how we can visualize the result in different way, and we can say, okay, this whole mechanism is going to work. Okay, and this is another way to visualize the result and see how effective your collaborative and the pre-process collaborative. So you can see, if you see the, so this is your initial partition matrix. When you apply the collaborative fuzzy clustering, you can see the order has been changed. Basically is 0.95 and this is 0.017. That's something different, you know. So when we apply the pre-process, you can see the order it's now is consistent with the original one. So now we can see with some changes here. Okay, so and this is again to validate the and visualize the prototype with collaborative fuzzy clustering and with pre-processed collaborative fuzzy clusterings. Okay, now till now I talk about the fuzzy C-mean clustering, collaborative fuzzy clusterings, and the pre-processed clustering. So these are more on theoretical side. Now we need to, and we also prove these this mechanism is working through different metrics and different evaluation criteria, such as a partition, a coefficient, classification, entropy, and the degree of approximation. And the degree of approximation we proved through the using the two different data sets. Now we need to apply this whole mechanism to the new systems and see whether it's really going to help us to improve the performance of the existing system, or it's just giving us some comparative results. Okay, now I will ask, is there any question related to fuzzy C-mean clustering, collaborative fuzzy clusterings, or pre-process collaborative fuzzy clusterings? I know this is more on, more on research side than it can be, but it's good if you guys can explore this topic or you can directly apply this whole technique into any application area that's possible. So you don't need to go through the whole things. You just use this whole mechanism and apply to, because there are not many people working in this area. So there are great opportunities. So even if you are working with the deep learning, you can apply fuzzy deep learning or collaborative fuzzy deep learning. You are working with any machine learning technique, you can apply this one there as well. So if you're working neural network, you can apply fuzzy collaborative neural network. If you're working with the SBM, you can apply fuzzy SBM. So you can apply anywhere, but you need to know how to apply that the right process. Is there any question till now? Okay, so if there is no question, so there could be two possibility. Either you guys totally understand or you didn't get anything. Okay, that's okay. Yeah. So now we can see how we can apply the pre-processed collaborative fuzzy clustering into different existing systems. So the first one we apply to the neural fuzzy inference system. So we replace the whole fuzzy mechanism with the pre-processed collaborative fuzzy clustering. So this is the overall structure. So the left hand side is your fuzzy neural inference network, and the right side what we proposed with the pre-processed collaborative fuzzy clustering. So you can see basically this is your neural network. So it's a rule-based mechanism. So here inference system, we need to generate the rules and the membership value, and then it's work. So how it's work? So basically layer one is your the input layer. Layer two is your membership layers. Layer three is a rule layer where define the rules. So once you define the rule, now in the layer four you optimize the layers, and then you have the output. So in the basic neural network, you have the input, then you have the hidden layers, and each hidden layers there is a number of neurons, and then each neurons you can update those neurons through using, there are many mechanisms to update. And after that you have the output layer where you have the input, and then you have some mechanism, feed forward or feed backward mechanism to update the value of the each neuron in the hidden. So I'll not go into details about the layer by layer, but this is the whole mechanism of the fuzzy inference network, and how we apply the pre-processed collaborative. So once you have the given data sets, what we did, we apply the so first thing we did, we divide the data set into two parts. So let's say you have a data set of 100 sample, and we divide data set into 50 number of sample and 50 number of samples. So now you have the two data sets, and we use this pre-process collaborative fuzzy clustering mechanism to let them collaborate each other, right? And then update one of the partition matrix and prototype of the one data set. And we just use the one data set instead of using your whole data set, where the whole data set contain 100 sample. We just use the updated 50 samples to train the whole architecture of the proposed model. So you can see there are benefit of using pre-processed collaborative fuzzy clustering. So instead of using the whole data set, you can just use the half of the data set, and you can train your models, and that model will be able to give the very comparative results. So while doing that, so you you are reducing the computational time as well. So let's say the original program with the whole data set is taking n number of times, but if you apply the collaborative fuzzy clustering, you are going to reduce the computation time as well. Even it can be a half or less, or even a little bit higher than the half computational time. So in terms of the computation time is much faster. And let's see whether we will get some more better result or no. So we can see. Yeah, so this is the overall structure of the neural fuzzy inference system. So as I explained, the layer 1 is your input layer. Layer 2 is your membership value. Layer 3 is more about the on the rule layer, updating the rule layer. And then finally, layer 5 is your output value. So you have the input and output, and then input, and then you have the output. So these are the internal layers which do some task for you. Okay, so these are the just a basic definition of the neural fuzzy inference system rule for layer by layer. So this is your input layer, and then this is your output layer, how it's looked like. So I'll not go through in line by line. I think if you guys are familiar with the neural network, the basic neural network, so this is the same. I mean, neural network. So where W is your associated weight of the each neurons. And this is just a definition of layer by layer. So layer 1, there is no computation involved because this is just your input data. Layer 2, you calculate the Gaussian membership value for each data points. And then in layer 3, basically you apply the fuzzy logic rule. So you compute and through the AND operator. And then layer 4, you normalize those and firing strengths and compute the number of rules and so on. Yeah. And layer 5, basically it's your defuzzifying the whatever you apply the fuzzification in layer 3, you need to defuzzify so you can get the output. Otherwise, the output will be different than the. Now, so in terms of the experimental result, we use the evaluation matrix that called root mean square error to see how your how the proposed method is going to work here. Okay. So we did a couple of experiment on the different data sets. So the first problem, this is the all problem of the prediction and the control related problem. So the first one, the data set we generated, that's called identification problem 1. So these are the equation which we use to generate the time series data set. And now what we did, so we generated a data set of 200 data set for training and 200 data set for the testing. And out of 200 data set for the training, we divided the data set into two different segments, data set 1 and data set 2, which contains just 100 patterns of each. And we use the learning rate 0 0.2, number of iteration 500, collaboration coefficient 0.5, and the total, we run this whole program for 30 independent run, and we presented the average value of this study run. So we can see, so once you divide your data set 1 and data set 2, now you perform the pre-process collaborative clustering, and then just use the only one data set to do the training. And that based on this training, you can see, and we compare the proposed, so the last row represent the proposed mechanism. So you can see in terms of the number of rules, so number of rules is very comparative. So you can see some of other proposed mechanism also uses the 4 number of rules, and this proposed mechanism also. But in terms of the training root mean square and testing root mean square, you can see the value is much lower than the previous proposed mechanism. So another thing you need to be identify here is that so this result, the training result, is just based on the half of the data set. So, and these results, the other results are based on the whole data set. So you can see, even though you are using the half of the data set to train your model, your training RMS is lower than the others. And also you can see the performance in terms of the testing of the data set, you have the better performance. So you can see this proposed method is effective in terms of solving this identification problem 1. Similarly, so this is just an visualization representation to visualize the results. So this is the desired, the blue is the desired, and the dotted red is your predicted. So you can see the predicted are, it's very close to the desired result. So this is almost equal. So that's why the root mean square error is very small. And this is your the error during the training. And this is result is based on the testing. So you can see for the testing also, you can see you can see the predicted output is almost close to the desired output. So that is the reason your root mean square error is very small. The second experimental we did with the identification problem 2. So this is the equation we used to generate the data set. And so for this experiment also, we generated 200 data set for the training and 200 data set for the testing. And further, we divide this 200 training data set into two different data set, that data set 1 and data set 2, that's contain 100 patterns. And we apply pre-process collaborative fuzzy clustering to collaborate these two data set and update the partition matrix and prototype. And we just use the only one data set, the update with the updated partition matrix and prototype, to train the whole models. So we use a 0.2 learning rate and 300 iteration and collaboration coefficient 0.5. And based on this experiment also, you can see the proposed mechanism. Even in terms of the number of rules, we have the lower number of rules. And so when you have the number of rules, that's represent how fast. So your whole computation is much faster than the others. And you can see in terms of the testing RMSE, you can see the testing RMSE is lower than the previous proposed mechanism. And this again, this is represent the desired and predicted outcome during the testing and the error. And the third experiment we did on the Mackie glass, again, we use 1000 for training and 1000 for testing, and divide the data set into two segments with the 500 for each data set and Further, we compare the result with the other different mechanisms. In this case, also we can see the proposed mechanism use the lower number of rules and give the better RMSE value in both training and testing. And this is just a training and testing. I think I just have 10 to 15 minutes more. And similarly, so I'll just give you how you can apply the pre-process collaborative fuzzy clustering into different application. So further, we applied pre-process collaborative clustering for the well-known Mamdani and TSK type of fuzzy inference system. So how we replace, so basically the below structure, the overall diagram of the fuzzy inference system. And then we, before using, so what we did, again, we used the data set divide into two segments. We applied pre-process clustering, and we provided the updated prototype and the granules that the granule value to the knowledge base system. And then we execute the whole programs. So based on that program also, so this is how the fuzzy inference systems works. I'll not go into details. We don't have a limited time. So this is the whole mechanism, how we apply the pre-process fuzzy CMIN clustering with the TSK and Mamdani one. So we divide the data set one to apply FCM separately, and then we apply pre-process collaborative fuzzy clustering. Then we update the prototype and partition matrix, and we use that updated partition and prototype to the Mamdani and TSK, and then finally you use the output. And these are just a result based on the identification problem one, and how when the dataset one collaborate with dataset two, and this is when the dataset two collaborate with dataset one. Okay, and this is the result we got. So in this case also we can see this is the original fuzzy based fuzzy inference system, and this is our proposed mechanism. So you can see both in terms of the training RMSE and testing RMSE, the proposed methods having the better performance compared to the original Mamdani and Mamdani type fuzzy inference systems. And this is also another when the dataset 2 collaborate with dataset 1. And this is based on the TSK type. And this is just a result. So we compared the original result with the proposed one. So you can see for different value of collaborative coefficient, we can see the proposed methods performing better in terms of training RMSE and testing RMSE when dataset 1 collaborate with dataset 2 and dataset 2 collaborate with dataset 1. So this is just again the desired and predicted outcome. Yeah, so I think so in conclusion, I think yeah, so overall, we can see here what we did. So we propose collaborative fuzzy clustering and the pre-process collaborative clustering that can help us to guide during the collaboration phase to order to provide the correct order of the clusters. And also we discuss, we proposes a novel fuzzy rule transfer mechanism for self-constructing neuro fuzzy inference system. Again, we apply this one with the different fuzzy inference system, basically Mamdani and TSK. And yeah, so the feature, the future work can be, so because as you know, the collaborative coefficient is a user defined. So we don't know what value of the collaborative coefficient is going to work and give the best result. So again, we can use the optimization techniques such as the particle swarm optimization, differential evolution, or gradient descent to optimize that collaborative coefficient that can give you the exact value which is suitable for the given task. Now I will open for the question. So thank you for attention. I know this is a little bit yeah.
Sir, we have a question in the chat box by Mohammed Shah Fahad. Is
Yeah.
there an
So is there an assumption to divide the data? There is no assumption. So you can basically randomly divide the data set. So when I say, let's say you have 100 sample, so you can randomly choose 50 sample for one data set and 50 sample for the another data set. So why we need to divide this data set? Because I don't have I don't have two organizations that can provide me the data set. So what we consider, okay, let's say this data set is the original data set. When we divide, we consider one data set belong to one organization and the second data set belong to other organization. So just to prove the mechanism is going to work. But in the real world also, I think you're going to have the same thing. So let's say a hospital, right? So let's say when the hospital do kind of a specific operation on particular disease, so they basically have a very similar data set into two different or three different hospitals. So while sharing their information, they can collaborate, right, using the collaborative mechanism. As we can see, they can't share the original information, so they can apply the fuzzy seaming clustering locally, and with the collaborative mechanism, they can collaborate each other to share the information, and then they can accordingly update their information and use the whole process, to train their model. Does your data set belongs to two organizations? So as I said, in our scenario, no. So we just had one data set, and when we divide the data set, we consider one data set belong to one organization and second data set belong to second organization. Yeah, so real world application scenario for neural fuzzy based on, yeah, so there are a lot many applications. So you can name it, you can apply everywhere. You can apply for the control system, such as so control system, knowledge based systems anywhere, so such as agriculture, biomedical, finance, marketing, stock prediction, and so on. Yeah, so neural fuzzy application can be, as I said, you can apply in the civil engineering. You can apply in civil engineering for the construction site, predicting the something happen, earthquake, so kind of control system, right? So in the area of the public health, in the area of mechanical engineering, in the area of electrical engineering. So there are a lot many application of the neural fuzzy.
Sir, in bio-inspired computing cognitions, can we apply?
Yes, yes. So if you can see, so you can apply genetic algorithm. So there are fuzzy based genetic algorithm as well. So you can apply this mechanism for bio-inspired optimization technique as well. Yeah. So yes, in neural network. So it's not exactly neural network. So this is the fuzzy. So whenever fuzzy comes, a fuzzy inference system, yes, you need to do the defuzzification. Otherwise, you can't get the desired output. So you need to apply the defuzzification. Also, we applied this mechanism with the in the brain-computer interface area. So we collected a data set for the autonomous driving car. So we did the simulation with the driving. So usually when you, let's say, to predict the drowsiness of the drivers, because when you drive longer, usually we get tired and you get sleepy and you get a dizziness. So there are highly chance to get some kind of accidents. So in order to do that, we did some simulation, and yeah, we applied this mechanism, and we found, yeah, so this mechanism is very helpful. So we are able to predict that dizziness or basically we can predict before, I think, around 10 seconds earlier. So that signals give you, okay, you are going to in the in kind of sleeping mode. So then system can give you the alert, and then you can probably park your car to take some rest, so it can prevent the accident and so on. So there are a lot many application, even in the autonomous driving car, this application can be useful, especially in the transfer. I think in the autonomous car, transfer learning is a very key topics to work on, and deep learning. Yeah. So of course, deep learning, you can directly apply these fuzzy things with the deep learning as well. Nowadays, I think there in terms there is one mechanism is very famous. It's called federated learning. So federated learning, people also propose to deal with the privacy and security concern. So I think fuzzy, this mechanism, you can further add there to propose new things. So there are many research problem you can create and probably apply these techniques to propose and do some experiment and see whether it's going to work on. But most of the cases, I think, yes, it will give you the better performance or very comparative result. Yeah. Is there any other question?
No, sir. I think there are no other questions as of now.
Yeah, so if there is no question, then I would like to thank you all for your attention and listening. Me hope you guys enjoyed or going to take something from here to apply into your research. So especially for if there are some faculty who are interested in research, and if you need help, I'm happy to discuss further. And so I think you must having my email address. So if you have anything you want to discuss, I'm happy to discuss further. And also with the student, if you are interested doing some research in the area of neural network, AI, machine learning, data analytics, I'm happy to provide some guidance.
Thank you, sir, for such an informative session, which led us through all the aspects in a detailed manner and adding on to the expectations of our audience. It was really a detailed explanation of the entire topic, and you explained us really well. Thank you for that, sir. Now, before concluding the session, I would like to give the vote of thanks. First of all, I would like to thank the VIT management for organizing this wonderful event for the students. I would like to thank our esteemed speaker for today's session, Dr. Mukesh Prasad, sir. We are really grateful to you, sir, because you took your time out of your busy schedule and took this amazing workshop. I would now like to thank our Dean SCAC, Dr. S. Poonkuntran, sir, AI Division Head, Dr. Soundarajan, sir, the Faculty Coordinator, Dr. Nilamadhava Mishra, sir, and all other faculty members and our esteemed audience for gracing the presence and making this workshop a success. Last but not the least, I would like to thank all our student participants who have registered for the event and have turned up for learning something new. So I would like to conclude our session on a positive note, and we have learned a lot. This is your host for the webinar signing off. Until we meet for the next year, have a nice day, everyone. Thank you, everyone.
Yeah, thank you.
you, sir.
Have a great day. Bye.
Thank you, sir.
Yeah, enjoy your vacation. Merry Christmas and Happy New Year to everyone.
Same to you, sir.
Take care. Bye.